We're going to discuss Euclid's algorithm. The aim is to find the greatest common divisor of A and B. We start by using the quotient remainder theorem to write A as B times some Q plus a remainder where R is greater than or equal to 0 but less than B, and we consider just positive B this time. So I'm going to show that all the common divisors of A and B will also be common divisors of B and R. So let's look at that. Suppose D divides A and at the same time D divides B. That means that D is a common divisor of A and B. Well, then this A can be written as D times some n, and this B can be written as D times some m. So the equation transforms to this equation. If I move this term to the left side and factorize D, I get D times n minus mq equals R. So we see that D is also a factor of R. So D is a common divisor of all three of these. Now, suppose instead that D divides B and D divides R. That means D is a common divisor of B and R. Well, in that case, A can be written as, well, D divides B, so I can write B as D times n. And D also divides R, so R is D times n. And that means that A is D times nq plus m. So D also divides A. So we see that common divisors of A and B will divide R, and common divisors of B and R will divide A. And that means the set of common divisors of A and B is exactly the same as the set of common divisors of B and R. And that means that the greatest element of that set would be the same. And that means that, in conclusion, the greatest common divisor of A and B equals the greatest common divisor of B and R. And that is the basis of Euclid's algorithm, as we'll see. Let's take an example where we try to find the greatest common divisor of 104 and 60. So I used the quotient remainder theorem to write 104 as an integer times 60 plus a remainder, which is less than 60. So in this case, it would be 60 plus 44. Now, the greatest common divisor of these two is the same as the greatest common divisor of these two. And I'm going to proceed and use the quotient remainder theorem on 60 and 44. So 60 is 44 times 1 plus 16. So the quotient is 1 and the remainder is 16. And I'm going to proceed. The greatest common divisor of these two is the same as the greatest common divisor of these two. So 44 is 16 times 2 plus 12. The greatest common divisor of these two is the same as for these two. And 16 is 12 times 1 plus 4. And 12 is 4 times 3. Our initial problem was to find the greatest common divisor of these two numbers. And using the quotient remainder theorem, the greatest common divisor of these two is the same as these two. And the greatest common divisor of these two is the same as for these. And the greatest for these is the same as for these, and so on. So the greatest common divisors of these two numbers is the same as the greatest common divisor of these two. However, 12 is a multiple of 4. So the greatest common divisor of these two has to be the value of the smallest one. And it's 4 in this case. And that number will always be the remainder on the penultimate line. So this is the greatest common divisor. So we go to the previous line. Once you have found a remainder of 0, go to the previous line, and this is the greatest common divisor.